Oh, hey, welcome back. And, heading in the 1.3 now, functions and graphs. And so, again, very simply with relations. And a relation is basically just a set of ordered pairs. So relations. What is this? It's a set of ordered pairs. So an example, let's say I have 2, 5, 3, 5, and then 2, 7, and then 1, 3. Okay. That's a relation right there. Just those 4 points represents a relation. And there's ways you can draw this out. You can do these graph things, these arrow diagrams, I think maybe they call them. On the left side is the domain. That's all the x elements. On the right, there's the range, all the y elements. Let's put the domain stuff in there. So we have 2, 3, and a 1. Or 1, 2, 3. And then we have the range elements, all the y stuff. So if we have a 5, there's a 7 and a 3. I should have put them in order. Oh well. So 1 goes to 3. And that's it. And then 2 goes to 5. And 2 goes to 7. And then we have 3 going to 5. Okay, so that represents a relation as well. Some things to note about this relation, in particular, that 2 splits off in the 2 different directions. And what does that kind of signify? I mean, that's going to tell you that it's not a function. For every x value, if it is a function, there will be one and only one y value. Okay, so whenever you see that splitting, it's not a function. The fact that there's 2 different things going to 5, on the other hand, isn't a big deal. Okay, that has to do with one-to-oneness and invertibility, which we'll talk about later. Okay, but in the meantime, this is officially not a function. And it's not a function because of that 2 element in the domain. Okay, so what is a function? That's where each x value goes to only one y value. Okay, so you could kind of look at the arrow diagrams or just even the set. Okay, trying to identify if the thing is a function or not, given the arrow diagram. Okay. So maybe if we draw out another set, 1, 2, 1, 3, and then 2, 5. Okay. Is this thing a function or not? Well, one kind of indicator is the fact that you have 1 written twice. As soon as that happens, you're done. Okay, that's not a function. But you can also, again, look at it in terms of the arrow diagram, and when you draw it out, you're going to see 2 arrows coming out of the 1. And just like above in my first example, it's going to mean it's not a function. Okay. So we have 1, 2. Over here we have 2, 3, 5. So 1 goes to 2, and then 1 also goes to 3, and that means it's not a function. Okay, so as you see that split, you're done. There's other issues like onto, is everything in the domain have a corresponding x value? Is everything in the range? Does everything in the range have a corresponding x value going to it? Stuff like that. You can really beat it to death. If you're going to go into math in a hardcore way, you need to study a little bit of set theory, and there are courses in set theory. There's some simple books you can read. If you want to, you can ask me in office hours, and I can say, oh, here's a book you can read on set theory. Anyways, if you actually graph the thing, so looking at the graph, you can use the vertical line test to tell if it's a function. And most students are familiar with this. So for example, the parabola going upwards is a function, right? Because every vertical line hits it at most at one point. So this is a function. So maybe you're asking yourself at this point, well, what is a function? Well, parabola is a function. Any line is a function except the vertical line. Okay, so this guy is a function. So things that aren't functions, and it doesn't mean it's bad, you know. Just because it's not a function doesn't mean it's bad. We're just trying to classify things. So here it's clearly not a function because a vertical line hits it in more than one place. So clearly this is not a bad picture, you know, there's nothing wrong with it. This is called an ellipse, one of these flattened circles, and they use that in modeling orbits of things in space, right? So it's not bad. We do have to work with those things, but it turns out it's not a function, just like any circle is not a function. Okay, what else can we do with these things? Evaluating, so we're going to have to do a lot of evaluation here. The consensus is that calculus is 99% algebra and 1% calculus. Okay, so a lot of the algebra in the beginning just comes from evaluating functions in weird ways. So an example, let's say f of x equals x cubed. Okay, and we want to evaluate something. So let's try maybe f of 3, right? So you put 3 into there, 3 cubed, 3 is 9, is 27, right? We can make it harder by putting maybe in some variables, right? So x plus 3. So x plus 3 in for x, so that will be x plus 3 cubed. Wherever you see x, you're going to put in whatever is inside this f of notation. Okay, so x plus 3 cubed is x plus 3 times x plus 3 times x plus 3. Foiling out the first two, you get x squared plus 3x plus 3x is 6x plus 9 times x plus 3. And then you have to kind of distribute these things. Okay, and then combine like terms. Long story short, will be x cubed plus 6x squared plus 9x plus 3x squared plus 18x plus 27. And then that's going to be x cubed plus 9x squared plus 27x plus, I guess, 27. Seems like the middle one should be 18. I'm just making sure my math is right. I think it's good. Let's try another one. So getting more to the point of calculus, the types of things we'll want to evaluate will be kind of things that look like this, x plus change in x. This change in x symbol is one symbol. Okay, so it's just like y or something like that. It's not delta times x. It's not two separate things. It's just one thing. Okay, that's just one thing. And some students won't even play around with it. They'll just replace change in x with h, okay, if you want. But anyways, plugging it into our expression, we'll have x plus change in x cubed, and then going through the rigmarole again. So x plus change in x times x plus change in x times x plus change in x. What is that? it'll be x squared plus x change in x plus x change in x is 2x change in x plus change in x times change in x is change in x all squared. Okay, okay. And then times this other one, x plus change in x. And if you know Pascal's triangle and the binomial theorem, you can just expand it using that. Most people don't know it by heart, so I do it the long way. Okay, so I have x cubed plus 2x squared change in x plus x times change in x squared plus, what do we have, x squared change in x plus 2x change in x squared plus change in x cubed. And that will be x cubed plus 3x squared change in x's. There's one there and one there, or two there and one there. And then there's one of these and two of those, so plus 3x change in x squared, and then plus change in x cubed. Okay. Okay. Ultimately, our goal is to kind of, if you remember from previous lectures, our goal is to find a slope formula for more complicated curves. Okay. And we'll accomplish that using the formula for slope, kind of. Okay. So we'll use this formula for slope, but instead of writing it that way, we're going to write it in a different kind of way. We're going to write f of x plus change in x minus f of x all over change in x. Okay. So, you know, you can agree that change in x is x2 minus x1, and at least it has some resemblance, right? You could think of this as your y2, and then this guy is your y1. But honestly, it's going to be able to give you a formula that will allow you to figure out the slope of these tangent lines to any point on the curve. Okay? So long as this expression turns out to be defined and there's some other technicalities we got to worry about. So what is going to become of prime importance is working with this new formula for slope. Okay, and they call it the difference quotient. There's some other stuff, calculus stuff we need, but it really is just basic algebra at the end of the day, and slope. You never thought that thing, maybe you think is kind of silly. Oh, everybody knows about slope. That's all calculus is to a large extent. It's just working the slope. So what did I say that formula was? It was f of x plus change in x minus f of x all over change in x. Okay. So this formula, very important, and will give us kind of a slope. And we want to evaluate this thing. Okay, so what do we have? F of x plus change in x will be x plus change in x cubed. Okay, that's just this guy right here. That's this. And then minus f of x, well, that's just x cubed, undefined from above, all over change in x. I've done a lot of the work already, right? I know what x plus change in x cubed is. It's x cubed plus 3x squared change in x plus 3x change in x squared plus change in x cubed, and minus x cubed all over change in x. Okay, simplify it, so the x cubes will cancel. Boom, boom. And we're left with 3x squared change in x plus 3x change in x squared plus change in x cubed. And for reasons to be announced later, we'll want to get the change in x out of the denominator. Okay. So you can factor a change in x out of the numerator, and you get 3x squared plus 3x change in x plus change in x squared all over change in x. And then you can remove those, and you'll end up with 3x squared plus 3x change in x plus change in x squared. Okay. Okay, and it turns out that the thing we'll be looking for later is sitting right here. It turns out this is kind of the slope function, which we'll call the derivative for x cubed. Okay, the slope function is 3x squared. Okay, the answer they'll want, obviously, in the software and on a test if asked for it would be the whole thing. But later on, we'll see it just turns into 3x squared. They'll let change in x be 0. Okay. Let's work a little bit with domain and range. Domain and range. And studying how functions the study of how functions change the domain into the range, and they're kind of connected. You know, you probably don't think of them as being connected, but it really is kind of a transformation. It's kind of like taking, I don't know, a can of Coke and smushing it into a different form, okay, using a function. You can really think of it that way. And there's patterns that come up, and you could study it in depth if you want to. Where are we at, you know, with regards to this study? Well, you probably were taught something about the domain, right? You were taught that the domain is a set of all real numbers except when? Well, the first case is when you have division by 0. The second case is when you have a negative under a radical. And then maybe even a third case is when you have something less than or equal to 0 in a log. Okay? So those three cases kind of are where we are with our studies. Right? Let's look at an example from the book, from the old book. F of x is square root of x plus the square root of 1 minus x. Okay. This one's a little more complicated. It's not just that we can't have, first off, from the square root of x, we need to make sure there that x is greater than or equal to 0. But we also need, what else? Well, we need to make sure, I'm trying to get my pen to work. We need to make sure that 1 minus x is also greater than or equal to 0. Okay, and what we'll need is the intersection of those two intervals. So from the blue one, we'll have to do a bit of work. Add x to both sides, you get 1 greater than or equal to x. And so x is less than or equal to 1. And then we'll consider the intersection. Okay, so that's basically if you were to draw these guys. So we would want to know where they overlap. So x is greater than or equal to 0. Then I'll plot x less than or equal to 1. And then I'll plot x greater than or equal to 0 and x less than or equal to 1. And sometimes we use the horseshoe symbol for and. Right? Okay, so here is 0. X greater than or equal to 0 is everything beyond there. Here is 1. Right? X less than or equal to 1 is everything to the other direction. And then the intersection is the overlap. So it looks like they are overlapping from 0 to 1. They both have 0, they both have 1, so we include those and write that with the bracket symbol. So at the end of the day, the domain is going to be the closed interval from 0 to 1. Okay. The range is always a little more complicated. Like I was talking about, how does the function really transform or sculpt, maybe is a better word, the original domain interval into new intervals. And the study of that could take, you know, quite a detour. It's quite a detour. And there are some disciplines which study it. One of the things that really upset me when I took calculus is there's all this kind of stuff, like how was I supposed to know that, or, you know, it's annoying, right? But if you keep taking math, you keep studying, I promise, after a while, the gaps kind of get filled in. I mean, there will be gaps in all of our knowledge. You can't know everything, right? But it's all out there, and it might come from a different class. You'll have to learn it there, and you'll pick and choose all the little pieces, and after a while, it'll come together like a puzzle. You just have to hang in there and trust your teachers and do your homework. Okay. So range, and sometimes you have to go above and beyond, right? Sometimes what the teachers tell you, they're just telling you that to help you get through. Maybe you have to go above and beyond what your teachers tell you, but I don't know. it all depends on you, what you want. So anyway, sometimes for the range at this point in our lives, we have to look at the graph. Okay? I think that's a sad thing, but it's true. We just don't have the tools, I think, to really get there for the range. But something like f of x equals 4x squared, you could back engineer this from basic facts about mathematics. In particular, x squared is known to always be greater than or equal to 0. Right? And you can even look at the graph of that. What's the x squared? Well, that's a parabola, right? And the x squared values, the y values, are always greater than or equal to 0. Right? Then you can take this inequality and multiply both sides by 4. That's not going to change anything. 4 is positive. 4 times x squared is 4x squared. 4 times 0 is 0. Okay? Well, what is 4x squared? Well, that's just your y value. That's the f of x. So for the domain here, it's all real numbers. You can pump anything into that, but the range is given right here after this back engineering. The range is going to be from 0 to infinity. Okay. Maybe a harder example is something you're not as familiar with, probably 3 over x. Maybe you are familiar. And I think I talked about it earlier in one of my lectures, way back, right? Oh, it's right here. It's this guy, right? This is just 3 times 1 over x. So all that does is kind of mess with the amplitude, so to speak. It'll stretch it vertically. So I kind of know what the picture is, right? And if you kind of know what the picture is, you can kind of guess what the range is. So the picture I'm guessing is kind of like this. So the range looks like it's going, the range is about the y values. Okay, so it's going from negative infinity all the way up to 0, but not including 0. And then it's going from 0 to infinity. Right? So the range here is going from negative infinity to 0. And to write this out, we'll have to use the union symbol. And then 0 to infinity. Okay? Okay. So sometimes you're going to have to look at the graph. A good place to look at graphs is Desmos, okay? Or on your graphing calculator. Okay, so you'll feel very uneasy about it, but I think if you keep taking math and you really get into the nuts and bolts of it, even on your own, there's probably videos you could watch, you could get better and better at that, and you have a better understanding of how these transformations are affecting the domain. So anyways, speaking of transforming things, we want to take a look at transformations of graphs. And this is all about working with kind of a fundamental set or a basis of pictures, and then we could use these as, I don't know, starting places to graph other graphs. And we'll have some rules that tell us how to move these graphs around in space, or in this case, the plane. The space is actually 3D. The plane is 2D. Okay, so 3 dimensions versus 2 dimensions. So anyways, what are some basic graphs? Well, obviously the equation of a line is there, but let's look at some other ones, right? So absolute value, the one we just did, the rational function. Parabola is obviously y equals x squared. The parabola's friend here, it's kind of half inverse, square root x. What else? The cubic, y is x cubed, should go through the origin. Its inverse, the cube root of x. And what else? Exponentials. Sure. Here's a logarithm, y equals ln x. We'll study that more later. The exponential, y equals e to the x. Okay, on and on. And the sine curves, you can think of those as fundamental shapes. And then to move them around in the plane, the transformations, how did those work? So you could add something to the outside, and that'll move it up or down. So if it's if you assume C is positive, then plus C will move it up, minus C will move it down. If you have y equals f of x plus or minus c inside, this time plus c will move it to the left, and minus c will move it to the right. What else? Constant, multiplying a constant on the outside, that affects kind of its amplitude. So if c is in between 0 and 1, then it's going to smush it vertically. If c is greater than 1, it's going to stretch it vertically. Okay. And then we could put a c on the inside, so you'd have f of c times x. So this time, if c is in between 0 and 1, it's going to be a stretch horizontally. If c is greater than 1, that will be a smush horizontally. Okay. And the best example of these is usually the trig functions, I think, especially for those last two cases. So I'll look at one of those versions. There is an order of operations, just like with PEMDAS. When you do these, you want to do your horizontal first, your horizontal shifts, and then your stretch shrinks. And then you want to do your reflections, and then you want to do your vertical movements. Okay, so sure, let's look at, well, very easily first, let's just look at maybe y equals x minus 1 squared plus 2. Okay? So first the horizontal shift, that minus 1 means it's going to go to the right by 1. And then secondly, there's a vertical, and it's going to go up by 2. Okay, so the right by 1 is because of this, and then the up by 2 is because of this. Right? Okay, so let's graph that. The original graph is just the x squared, so that from above is this third graph here. So I can start with that. Right. And then I can just move it right 1 and then up 2. Okay, so my new graph would be sitting about right here, and it would look like this. Okay, and I don't have to go through this big process of getting a bunch of points or opening up my calculator or anything like that. Okay, so let's do another example, maybe a little harder, which is a trig function. We have a review section in trig coming up, so you could watch that too as well. But I like these because it kind of helps you remember the vertical and the horizontal stretch shrinks. Okay. Okay, so first off, are there any horizontal left-right movements? And there's not. Okay, so no, that would be inside the sine function in here. Secondly, are there any stretch shrinks? And yeah. Heck yeah, right? So first, the vertical. And that, what is that? That's just the amplitude. Here our amplitude is 2, right? On the outside, that 2 times the sine is going to give you a vertical stretch of 2. Vertical stretch by 2. Okay. Then the 2 sitting on the inside is going to give you a horizontal stretch. And actually, in this case, it'll be a smush, right? Or a shrink, if you'd rather. And usually how you figure that out is by wedging the 2x in between 0 and 2 pi, right? That's one full period of the curve. And then solving for x. Okay. So it went from one full period between 0 and 2 pi, and the 2 smushes it to be one full period from 0 to pi. Right? So again, originally 1, 2, if I'm going by pi over 2, originally it would look like this, but then when you put in 2x, it'll smush it, so it then looks like this. Okay. Smush horizontally. Then thirdly, reflection, that's the negative in front of the sine function here that I'll circle in green. Okay, so that's going to do a reflection about the x-axis. It's on the outside. I guess I didn't note those in my, yeah, I did, sorry. I apologize. Let's zip back there real quick. So if you have y equals negative f of x with the negative on the outside, look what we have. It's an x-axis rotation, so I'll just draw it like that. If you have y equals f with a negative on the inside, it's a y-axis rotation. Okay, so it'll go around like that. Okay, so let's go back. We have the negative on the outside, so that means it's going to be an x-axis rotation. And then finally, the 3 on the outside here, the plus 3, this last thing here, is going to shift it up. So vertical up by 3. Okay. Okay, and let me rewrite it because it looks pretty nasty right now. 3 minus 2 sine 2x. Okay, so let's graph that going. Usually I split the period into 4 places. Okay, so 0 to pi, if I split that into 4, it's pi over 4. So my tick marks will be by pi over 4s. The amplitude I said was 2, so I'm going up 1, 2, down 2, and there's a flip, so it's going to originally kind of look like this. Okay, so I'm flipping the sine function, and then I got to go up vertically by 3. So 1, 2, 3 is kind of the new center, if you will, and then it's going up and down by 2. Okay, so it's going to look like this. And there we go. And then it goes on and on forever. Okay, so there's that. Composite functions. So we deal a lot with sort of doing things to functions themselves. Right? We'll be putting functions inside of other functions. And yeah, so composite functions. So the notation f of g of x just means you're putting g inside of f. G of f of x just means you're putting f inside of g. Like that. Okay. Okay, so let's look at 67, or an example. It's not necessarily 67 anymore. We have f of x equals x squared, and then g of x is the square root of x. Okay? And the problems in the software will ask you to find the composites. So f of g of x, and then are they the same? Okay, so okay, here we go. F of g of x. So I'm putting g inside of f. Okay. One thing to note here is there's an implied domain because there's that square root there. And even though the square will get rid of the square root, there's an implied domain. You can't just put anything into g, right? The domain will be from 0 to infinity. So although the equation y equals x is a line through the diagonal, f of g of x is actually just a half line, right? Okay, let's look at g of f of x. So this time I'm putting f inside of g. Okay, the square root of x squared is not equal to x, right? Note that the square root of -3 squared is not equal to -3, for example. Okay. In fact, it's equal to +3, right? Because -3 squared is +9, and then +9 squared is 3. So you can't just write x, okay, like we did before. It won't work. So what are you supposed to write? It's actually the absolute value of x. Okay? And in this case, the domain is all real numbers. Okay? You can put anything into that thing, and there's not going to be an issue. There's no radical or anything like that. So these two guys are not the same. In particular, you can graph this thing. The absolute value of x looks like this. Okay. So no, composites are not necessarily ever going to be equal. Sometimes they will, and when they are, if they're both equal to x, in particular, for x's in the particular domains, then they're inverse functions. Okay, so these seem like inverses, but technically they're not. And we'll talk about that more later on. If you look at the pictures, f of x looks like this, and g of x is this guy. They're not inverses because f of x is not actually invertible. It would have to pass the horizontal line test, okay, and it doesn't. And we'll talk about that later. It's one-to-oneness. Okay, let's move on. Okay. So even and odd functions, we've kind of already talked about this with symmetry. Okay, symmetry applied to all relations, but even and odd only applies to functions. Okay. So in particular, the even symmetry is the y-axis symmetry. Okay, and you can test a function by putting -x in for x. So if you plug -x in for x and you get out f of x, then it's even. Okay, so for example, f of x equaling x squared. If I put -x in for x, I get -x squared, which equals x squared. Right? A negative squared is positive, and that equals f of x. So this thing is even. Okay, so in this example, f of x is even. Oddness then. If you plug -x into the function and you get negative f of x back out, then it is odd. Okay, so an example, let's make a harder one, something like x times the square root of x squared minus 1. Okay, so put negative in for x, and you get -x times the square root of negative x squared minus 1. Which is equal to -x times the square root of x squared minus 1, which of course is just negative f of x. Okay? In other words, this thing is odd. Okay, what else do we have here? Determining if something is a function. Did we talk about that? Oh, sure. So so let's say you're kind of worried about the vertical line test. Maybe you're dealing with something that looks funny, and you're having trouble graphing it with your calculator. For example, this guy, y squared equals x squared minus 1. Okay. In your calculator, you have that y equals menu, so y1 is, y2 is, y3 is. And if you tried to plug it in there, you wouldn't be able to, because you can't graph y squared equals something. They're all in terms of y's. Okay, so how would I even do a vertical line test if I didn't know what it looked like? Assuming you didn't know about Desmos. Okay, so you could try to solve for y, and then you could draw each one of the answers. So the square root property says if y squared equals blah, then y equals plus or minus square root of blah. Okay, so this has two separate functions, and you could take a look at it. It'll turn out that it's a circle, right? So, well, it's not a circle. Sorry, I apologize. It's a hyperbola. But as soon as you see one of those plus or minus things, generally what the books will tell you is to automatically stop. It's not a function. Okay, so it's not a function. And why? Well, it's because for any x value, well, for 99% of the x values, there's going to be two y values. So you end up getting that split thing in your diagram, right? So for one x value, it's going to go to plus something and then minus something, right? And that'll cause it to not be a function. Okay? So as soon as you see those plus or minuses, you can kind of say it's not a function, unless you have some weirdly restricted domain issues. So there's always some weird issues that can pop up, but usually it's not a function. Okay. What else? Maybe look at the homework. WebAssign. Where are you? Got that done. So WebAssign, we're now in 1.3, I believe. Let's make sure I've prepared you, and I don't like to send people out into battle unprepared. So evaluating functions, there's the difference quotient thing. I did that one directly in the notes, so you should have that answer. Domain and range, okay. Vertical line test. So that's one we could do what we just did. You can try to solve for y, and y will equal plus or minus something, so it won't be a function. This is using transformations. So this going from the black to the blue is moving it by 3 to the right. So it's going to be square root of x, and then, yeah, minus 3. Okay. Some more transformations, evaluations. Oh, be careful with whenever you have, so I noted above that the square root of x squared is absolute value of x. In general, that's true whenever the root type and the exponent type are even powers. So if you have this, that's also absolute value of x. Okay. If you have a cube root of x cubed, no, that's just plain old x. Okay, but when it's even, so if you have the 6th power of x to the 6th, that's going to give you absolute value of x. Okay, so I think you'll see that in this problem here, number 10. What else? Some odd and even stuff. Odd, even. Tops and bottoms of circles. So if you have something like x squared plus y squared is 25, it's a circle centered at the origin. Okay, you can rewrite it as two functions. You can write y squared equals 25 minus x squared, and then you can solve for it. Y is plus or minus square root of 25 minus x squared. So these are two functions, right? There's y equals positive root, which is square root 25 minus x squared, and then y equals a negative root, negative 25 minus x squared. So visually, what's the difference, right? Well, the first one is the upper half of the circle, and the second one is the lower half. Okay? So that's the difference. What else? Oh, that's about it. Okay. I hope that will get you through it. We can look, sure, let's look at that last one. 9 over x minus 5. We want the domain and range. This is basically just a shifted version of our rational function. This guy that looks like y equals 1 over x. The asymptote in this case is where x is 0, right? Where the denominator is equal to 0. That will give you the asymptote. So you can think of this in two ways. You can think of it as a stretched version of this, and it's been shifted over by 5, right? Or you can think, well, the asymptote is going to be at 5, because if I write x minus 5 and find where that's equal to 0, it'll be x equals 5. Honestly, multiplying it by 9 isn't going to change the shape too much. It'll just sort of stretch it, and you could do some point plotting if you need to know exactly where it goes. But in the end, it's just basically going to be a shifted version of this original graph by 5 to the right. Okay, and then there's a little stretching, but honestly, it's not going to affect the graph too much. Okay, so let's leave it at that, and I'll see you next time.